Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the first lecture of the course Aerospace Structural Analysis. So, I am Meera Mitra, a professor in the Department of Aerospace Engineering, IIT KANPUR. So, you must have seen in the web page of this course, the syllabus of the course is given, and also the weekly breakup of the course is also given, explained and given in the web page of the course. So, I will not again talk about that and directly start into the introduction of the course. So, this will be a 20 hours course, and the first week would be an introductory lecture talking about the brief introduction of aircraft structure, how aircraft structures are very much distinct from other civil and mechanical structures, what are the important considerations that one has to keep in mind while designing and analyzing aerospace structures or aircraft structures, and what are the basic concepts that we need to know before we can analyze and design aircraft structures, and a brief history of how aircraft structure developed, and several terminologies and several components of the aircraft structure that we need to do. So, this will consist the introduction part of the course, which will take about a week to complete. So, let me go. I always start the course on aircraft structure or aerospace structure with this slide, with this clipping that I have. So, first let us try to understand that why are we studying aerospace structures as a special, as an entirely one course on its own, and why not theory of elasticity and or solid mechanics is enough to understand aircraft structure. Why do we have a special course or a dedicated course on aircraft structure? So, what we will be doing in the this course is that we will be utilizing the already known concepts of solid mechanics, structural mechanics and theory of elasticity to analyze and design aircraft structures, which are primarily thin wall structures. So, most of in the slides that I will be using for the introductory part of the course, I will be using several figures to give a bigger picture or a broader picture about the motivation, the importance and the fundamental concepts of aircraft structures. I will be using some pictures and photograph from these two books, textbook, one by Perry, Aerospace Structure, and other by Professor T. A. Wishar. He is a faculty at Purdue University. His book is available as an open source book. So, I have taken some pictures from this book, and I give due acknowledgement to all the material that I have taken from his open source book. So, this is a clipping that have been published in New York Times in October 9, 1903. So, I will tell a brief history about it. So, a lot of we all know about Wright brother, the first powered heavier than air aircraft vehicle was designed and demonstrated by Wright brother, the famous Wright brothers. All the modern day flight that you see have been started by Wright brother. Perhaps all of us know about it. But before Wright brother demonstrated their successful flight, there was a large effort that was directed towards development of aircraft or lighter than aircraft, heavier than aircraft, and one person, Samuel Langley, is one of the pioneer of aircraft structure, and he had put a lot of effort in designing aircraft, and Wright brothers and other his successors have learnt a lot from the work done by Samuel Langley. So, his work was supported by a lot of funding from the government, but there was a serious failure of his flight demonstration in 1903, and that had resulted to a lot of skepticism and criticism of funding of aircraft design and development. And this is a clipping from New York Times, which says that this is a clipping from New York Times that says that the flying machines or the aircraft which will really fly will take a combined effort from scientists and engineers or mechanicians for 1 million to 10 million years from the date given 1903. Okay. This criticism came in media immediately after the failure of the flight demonstration by Samuel Langley. So, Wright brother used to maintain their diary of the progress and the development they used to make. So, in the October 9, on the same day, in their diary it is noted that they started unpacking to build their aircraft, and as all of you all know, the first flight happened just few months later on December 17, 1903. So, it shows that though aircraft seems to be a very complex engineering and a complex design, a very thorough understanding and a very efficient use of the already known solid mechanics and structural mechanics concept can actually help us to attain the rather complex looking design and analysis with much ease and much elegance. So, what we need is to understand the basic principles of solid mechanics and structural mechanics and theory of elasticity, and just translate them to the concepts of thin wall structure or aircraft structure. That is what we are going to do in this course. So, this is kind of summarizes the motivation of the course. We will learn the concepts of solid mechanics, structural mechanics and theory of elasticity towards, with the application in mind that we will be finally designing and analyzing thin walled aerospace structure, which though may look very complex, very advanced, but would just require a very clear and thorough understanding of the fundamental concepts of mechanics. So, with this, let me move on to the next slide, which shows. So, this is another figure that we have. So, this shows the airframe of a Boeing 767. So, this shows the airframe of a Boeing 767. So, so you can see that the airframe or the skeleton of the Boeing 767 is utterly complex. It has several components interconnected with each other, and it can be as complex as one can think of. Okay. And to just give an idea, a Boeing 767, the airframe of a Boeing 767 has 3.1 million interconnected parts with 85 miles of wiring. And this parts, these structural components of or the structural parts of this entire airframe comes from around 1300 vendors. So, this information probably gives you an idea about the complexity of the aircraft structure, about the diversity or about the variedness of the component, and at least large number of different material, large number of different joining techniques, welding techniques, manufacturing techniques goes into building the aircraft structure. So, different form of material, different form of manufacturing technique, different forms of interface makes this aircraft structure even more complicated. So, let us move on to the next slide. So, this slide just gives you an idea about the final product that we are looking forward to design and analyze. But the beauty is that though this final product may look very complicated, it can be easily tackled. It just looks complicated, it is not very complicated. This can easily be tackled by simple knowledge of mechanics and simple knowledge of elasticity. Now, in this slide itself, I want to clarify certain point. So, I have been teaching aerospace structure for quite some time. So, the students always ask me this question, that in the course we mainly talk about beams and a little bit of plates and cells, a very small amount of plates, small portion of plates and cells, mostly about beams. So, a obvious question that comes from the student is that why are we trying to study beam, trying to design beam and some plates and cell, when the final structure that we have to deal with is this complicated. Now, there are two answers to this question. The first answer is that the beams are the most fundamental building block of a structure. So, unless you understand beam, plates and cells very thoroughly, you can never understand the advanced structure that might be there in an aircraft, in a spacecraft or in any other complicated structure. So, we have to understand the fundamental building block or the fundamental structures which are beam, sometimes a plate and a cell, and so that is the first answer to the question. The second answer to the question is that as we go through the course, one will realize that most part of the load bearing aircraft structure are beam like structure. They are thin, slender structure with the cross sectional dimensions being much smaller than the length or the lengthwise dimension of the structure. So, they can be very well modeled as a beam. Okay. Some part of the aircraft structure is of course a cell and a plate, but major part of the load bearing components of an aircraft structure are beam like structure. So, by understanding and by modeling beams effectively, we can model and analyze a large portion of the components of an aircraft structure. Okay. So, that is the reason that in the course which is aerospace structural analysis, we will mostly deal with beams, thin wall beam and some thin plates and shell at the later part of the course. Okay. But majority of the course we will be dealing with analyzing thin wall beam and thin walled shells and plates. So, with this, let me move into the next slide. So, let us next understand what is the design requirement, what do we need if we want to design an aircraft structure or aircraft structural component. So, the first requirement is to know the load. The first requirement is to know the load of the structure. So, here what we need to do is that we need to know the load definition that the structure is going to encounter. Like any other structure, like a machine part or a civil structure like bridge and building, we need to know what are the loads that are going to come on the aircraft structural component before we can design it. So, this load that comes on an aircraft structural component can be aerodynamic load, can be the load due to maneuver of the aircraft. Okay. The G load that we conventionally known, we commonly know that aircraft structure or space structure often encounter this G load or the inertial load that occur due to different maneuver of the structure. There would be impact kind of load when the structure, when the aircraft lands or takes off. So, all these forms of loading that are going to come on the structural component of an aircraft should be known clearly before we can go ahead and design the component. So, certain part of the aircraft will experience only aerodynamic load, certain part will experience an impact load, certain part will experience a maneuver load most. So, this things has to be known clearly in advance before we can design the structure. The second thing that we need to know is that how the structure will be shaped. Now, different component of an aircraft will be shaped in a different way based on the functionality of the component. Like the wing will have an aerofoil kind of shape, the fuselage will have a certain part of the fuselage will have a cylindrical shape. So, this shape is usually governed by the maneuver the aircraft will undergo, the aerodynamic load that the aircraft will be undergoing, and therefore, this requirement of the shape will be given to us from the aerodynamic group of the aerodynamic and propulsion group of the aircraft design. So, as a structural engineer, we need to know this beforehand before we can go ahead and design the structure. So, the third thing that we need to know is the description of the environment where the structure will operate. This is also similar to that of a building or a bridge or a machine part. So, if we build a building in India, whereas if we build a building in Japan, we have to build it with a different material, because as we know, as the recent unfortunate event has also happened, Japan is much more vulnerable to earthquake. So, the building there will be built in with different material as compared to the building material that we use in India. So, similarly, if we are using the aircraft in say if it is a navy aircraft, if we use it mostly in the in oceans, in seas, then the aircraft will have to withstand a lot of moisture or humid environment, and therefore, we have to select the material of the aircraft structure in such a way that this moisture can be resisted. Similarly, if we are building an aircraft which will be used in very hot region like that of a desert, then we have to select the material accordingly. So, this requirement also needs to be understood and needs to be this information needs to be provided to the structural group of the design team of the aircraft before the structural engineer can go ahead and design the aircraft structure. So, the Fourth point, which is also very important, as you have seen in the earlier slide, that the aircraft structure, the skeleton or the airframe contains of multiple interconnected parts. And as we all can know, and as our intuition says, that whenever there is an interface, that is probably one of the weakest spot of the structure. So, and as aircraft structure has a lot of joints, interfaces, welding, we need to have a clear knowledge or information beforehand about these interfaces and joints before we can go ahead and design the structure. We need to know where certain equipments will be placed, because if a very sophisticated equipment like a GPS monitor is placed somewhere, then that part of the aircraft structure should experience the least vibratory load, so that the reading of the sensor or the device should not be disturbed by the vibration of the structure. So, all this information has to be there with the structural engineer or the structural designer of the design team before they can go ahead and design the structure. Now, the second question, as I told in the beginning, that aircraft structure is very much complex, as you have seen from the previous slide, and as our intuition says, it is very distinct from other civil and mechanical structure. Though I have said that these are complex, the basic solid mechanics and the theory of elasticity will help us to tackle this complexity as well, but it is important that we understand and appreciate the complexities associated with aircraft structure. The first complexity is lightweight. On first thought, you will be able to understand that lighter weight is a criteria for almost every structure, because lighter the weight, lower the cost. So, we always want to make a bridge lightweight, building lightweight, mechanical machine lightweight, because lightweight means lesser material means lower cost usually. But so similarly, aircraft also needs to be lightweight, but for aircraft, weight is a overriding factor. At every step of design of an aircraft structure, one has to check the weight, unlike any other structure. So, weight is the most overriding factor in an aircraft structure. Such weight constraint is not experienced in any civil or mechanical structure. Here in aircraft structure, higher weight does not only mean higher material, higher amount of material involving higher cost, but higher weight also means higher fuel consumption, lower capability to carry commercial weight, and higher the cost of running this aircraft. So, for aerospace structure and aircraft structure, it is at every step of the design, there is a person who checks what is the weight penalty because of any design that we do or any change that we do to the aircraft. So, next concern is that unlike a civil structure or a mechanical structure, a aircraft structure undergo a variety of load, which could be an inertial load, a vibratory load, an impulse load during landing and in-flight maneuver. On the other hand, on the contrary, a mechanical machine or a civil infrastructure never experiences this variation in the kind of load that is experienced by the structure. This makes aircraft structure much more difficult to analyze and design as compared to its counterpart. So, that makes it very complex to analyze and design. The third point is that it needs to operate in extreme environment and wide range of temperature. So, while the aircraft is in the ground, while it is doing the takeoff and taxiing, it experiences certain ambient temperature, which is a normal temperature of 20 degree centigrade or so. But as soon as it is in its full flight, it is at a very low temperature. So, we have to choose a material which can withstand a moderate temperature as well as very low temperature. Similarly, the material that we use for aircraft engine also needs to experience a wide range of temperature, also needs to withstand this wide range of temperature. And then there are this variation in moisture content. Aircraft which has been designed for a dry environment may need to operate in an environment which is humid and full of moisture. So, the material should be able to perform equally well when the environment is dry, whereas also when the environment is humid and has a higher moisture content. So, this variation in environmental condition, this the need to perform at extreme environment also makes the choice of material and the design of aircraft structure much more complicated. So, before we go into further detail, we will talk about the brief background of how aircraft structure developed. So, aircraft structure was first octave had been explored even before Wright brother, before the first flight by Wright brother. It was explored thoroughly by several engineers who made their attempt to make flying machine. One person who we should note and we should mention is Octave Canute. He was he was an engineer in railways and has to his credit the design of several bridges, advanced design of several railway bridges. So, after he retired from railway, he invested his time in developing flying machine. So, the first aircraft structure developed by Canute was made of truss structure, which was wrapped by fabric to give it a aerodynamic configuration. So, he started the use of truss structure to build the aircraft structure. The benefit of using truss structure is that it is lightweight, it's extremely lightweight, and it can be any component, any part of the aircraft structure can be replaced without changing the entire aircraft structure. So, Canute is called the father of aerospace structure, and after him several engineers and several designers has further evolved the design of aircraft structure. So, from the next lecture onward, we will discuss how aircraft structure slowly evolved from a truss structure developed by Canute, and finally, the modern day aircraft, how the modern day aircraft structure is the most efficient and most commonly used design that are used nowadays. So, with this I will end this lecture. Thank you.